Alright, time for another draftphysics.com, debatephysics.com, also video presentation. So, this Eugene Khutoryansky, anyway, I used to make videos, I can't remember what it was called, but it was some kind of generic-y, phantasmagorical name of the channel. Anyway, so instead, he's using his real name, which is bizarre, just because it's kind of a bizarre name. Anyway, complicated, hard to say, all that kind of crap. But anyway, doesn't really matter. Now has 1,000,000 subscribers. The videos are well produced and all that. I've tried to contact him a couple of times, no response. And it's just irritating that you really can't argue their physics with them. They're just science presenters. They're just talking heads, and it's all done in an environment of isolation. And once in a while, they'll engage in some sort of argument between each other, but that's it. They have very controlled rules about who they'll engage with. Anyway. So yes, it just creates a very unscientific atmosphere of it's not really a democracy of any kind, or there's not a some sense of some equal speech rights, and of course it never has been. It's always money can publish and money can talk more. So anyway, I don't want to get into a bunch of that. But science should be above that, and it's really not. Alright, anyway. So, this video is on laws of motion, and, as defined sort of by Newton, who didn't elaborate too extensively. That's, needs to be stated. But I think the context is wrong. I mean, I think it always should be pointed out the first law of Newton's, in a sense, was his argument that it's 3 dimensions of physical space that everything exists in, and forces are real. They're not just relative concepts. They're relative in a physical way, in the sense that 2 objects can have the same condition and then have differences in that isolation of having the same conditions. But they're in 3-dimensional space, and one of them is different than the other one. The differences are real. The vectors of motion. The difference in their vectors of motion. And he proved that with spinning objects. Spinning objects kind of prove, logically make a pretty good proof that there's no way you could reverse it and say the universe is spinning. It would be silly to say it. And second, you would have no expectation that if, for example, you spun 2 balls hanging from sticks that could swing out as they spin, that was the example Newton gave, was, spinning the universe would not cause the 2 balls to move out. And spinning the universe wouldn't create more magnetism or gravity or some sort of mechanism to cause that reaction. And so the action has to be internal here. It has to be a real thing happening to the spinning object, not happening to the universe. Alright. Reversibility is probably the better word to use. So look, it's unfortunate that they're going to force physics to either be in these 2 forms. Something written in the 1600s, okay, conceptually, and something after 1950. And there's just nothing in between. So it's either this wooey quantum garbage or a kind of ignorant, okay, but well-reasoned physics. So classical physics is well-reasoned, but poorly evidenced, okay? And modern physics is unreasoned and no evidence, frankly. No substantial evidence, no justifying evidence. All right, so let's just get to it. So it's all of this. This is science. We have to. So it's nice to illustrate things. I like drawing. So drawing is good, illustrating is good, but this is all just formulaic colors, picture. It's manipulative.
There are 3 laws that govern the motion of everything in the universe.
All right, so this whole whatever this is, the owl thing. The first law is almost so stupid that you'd say, oh, let's not even bother with that. The fact that things are in conditions and they stay in the condition until something changes the condition. So it's basically saying the law of cause and effect or something. The law that requires interaction for things to change. Duh. Yeah, I'm playing it. It's not my fault.
The first law states that a body at rest.
All right, so this guy Eugene makes these videos, and then this is all part of the formula. And then he has this woman read it, and it's all yeah, it's all they're very nice animations and all that stuff. A lot of work goes into all that crap, but the statements are so rudimentary, and it's science. And science should be kind of cleansed of this kind of it looks like propaganda kind of thing.
Rest will stay at rest, and that a body in motion will stay in motion,
indicating that the motion is something it has. Okay, certainly. That it's a condition it's in, you could argue, and that the rest of the universe isn't the thing moving, it's the thing moving, blah, blah, blah. There are real things in the universe that are at rest, and there are things in the universe that are moving some real 3-dimensional vector in 3-dimensional space.
Without a force, all objects will continue moving in the same direction with the same speed forever.
All right, so that you can't say for sure. Now, obviously, I could argue that photons seem to obey that rule, but you could argue what happens at the end of the universe, and you could make but yes, it seems the forces are always traveling the speed of light, and it doesn't matter if they've been traveling for billions of light years. They're still going the speed of light. So there's obviously the forces, the stuff going the speed of force. That stuff doesn't slow down. But whether or not matter retains its velocity, we really haven't tested. I mean, not to any extent. I mean, we don't, we just, as a practical matter, don't live long enough. Haven't lived long enough. Humans haven't even been around long enough to be able to truly test something that could take millions or billions of years to happen.
Objects here on Earth slow down only because of the force from friction and air resistance.
Okay, so he's calling it a force, and there's just no point in calling it a force. It's just so obvious what's really happening, so why not just say it, what's really happening? Okay, there's no counter force of friction. Details. So anytime, it's like I use this dropping example. All right, so I could just drop something, and it's going to free fall. It's going to obey Newton's laws. 1 unit of distance in 1 unit of time, and then the next unit of distance will be 3 units of distance in 1 unit of time, and 5, and then 7, and so I could put a wall right next to it, very, very close, and no friction. No, it's not making contact. But as soon as I make the falling object have some reason to contact, that is, I apply some kind of wind or force and cause it to hit the wall, what it's going to do is any force that's in this, any mv, okay, velocity being the really important part, is going to is going to create interactions. And what's an interaction between? It's an interaction between the little tiny things inside of the object, right? The object is made out of these little bits. And some of the little bits, okay, now all the little bits are going to get this vector going down. The little bits are all being accelerated by the gravity. They're all got the velocity. They're all staying together. The object stays in one piece as it gains its acceleration. And so what's going to happen when it hits the wall? Some of the little bits are going to hit the wall, the little bits that make up the wall. And so now you're going to just create interactions on this small scale where the atoms here, the electrons, you could even argue, and the electrons here are going to interact with each other. And what's going to happen plainly is this change, this difference in their vectors. These have zero velocity and these have a definite velocity. They have a definite vector difference, so their arrows look different. You could say, how do you draw the non-moving arrow? Okay, I guess you just use a stick. There's no way to do it. The zero velocity arrow. Oh, I guess I just use well, that would still be cheating because it indicates a direction. I guess I could use this little square. Okay, so this is what's happening. You have these little bits, some of them with this arrow, this vector, and it's going to interact with the zero vector bit. And all that's going to happen is those two conditions are going to interact and essentially combine. And you have every expectation that you're going to give the thing with the zero vector some vector, okay, and that you're going to alter the thing that hit vector. And so now you're going to have new vectors with new intensities. The length of the line will be different, the size. So some of the bits are going to just start interacting. So it's just like a temperature gradation where you're just going to say that, yes, some bits inside of this air are colder and some are hotter. And so if I interact with something, the hotter bits can migrate, and the hotter bits here can heat the cooler bits in this section, and it's going to blend together in a way. And so the same thing happens, a similar thing happens when these two things interact. And so all you're going to do is you're going to take the force and you're going to push it into these objects, and they're going to move in all kinds of directions. So now direction isn't going to matter, because when one hits and you change this vector, now this vector will hit and change the vector to some other direction, and this next one will happen and it'll change to another direction. So now you're starting to change an arrow that was going solidly in one direction, and when you give it to the wall, it's going to be in all kinds of directions. Okay, so now you have motion, okay, that's basically heat. So you're going to just make a conversion of a mass moving a velocity, a bunch of little masses moving a velocity, and you're going to exchange it, and now they're going to have all in one vector, and now the vector is going to be broken up. So you're going to have you could say you're going to have a vector arrow that was going to be this, and you're going to change, because of the friction, into a bunch of this. And so this arrow is going to get smaller because you've lost some of this motion, and you've given the motion to pieces in the wall. And if you add up all of their little bits and add it to this, all of this, okay, will still equal this. So these, the force essentially is in the object moving. It's going to be proportionally shared, or in some way shared, with the wall, and there is no counter force of friction. There's just the fact that you could say the ball falling has $10, okay, of motion, and it's going to give $3 to the wall. And in giving $3 to the wall, it's only going to have $7. So there's no equal and opposite reaction. There's none of that stuff. There's just something automatically loses. It's automatically changed when it changes something else. It can't change something else without changing itself. So it has to, for it to lose, it has to give. Or something has to take. But that's it. So I think the underlying physics is this, that everything should really be understood as being made out of elemental pieces. And the only thing that makes one form of matter different than another form of matter is how rigidly stuck together their pieces are. So you could argue that some things don't separate. Their little pieces won't break off easy. They don't separate. They can't give a piece of their energy away because every little piece, none of the pieces will break off, so to speak. And other pieces of matter the little pieces aren't held together well at all, and you can fracture them quite easily into a bunch of separate pieces. So some are held together tightly as one object, and some aren't. Alright, I think that's acceptable. Context. Facts. I would argue that this is better physics. So you're just basically saying, look, when the block's moving, it's rubbing on the surface is the energy is being transferred. So it's just like a bowling ball hitting the bowling pins. The ground is a bunch of bowling pins. You've got to use the energy of the ball to move the pins. The ball can't keep its momentum and give it away. So as it gives motion to the ground, it loses motion. But there's no force of friction. Same with the air. So the air is a good example of what I was talking about, the mushy stuff, the stuff that falls apart easy. Air molecules are very independent. They're not stuck to each other, so you don't have to move all the air. You can just move little pieces of the air and just directly transfer little bits of your thing will hit the little bits in the air and just transfer share conditions. So the longer they're in contact, the more they share. The less they're in contact, the less they share. So you can have an equal exchange of your condition if you're stuck to each other a long time. But if you're just hit for a second, you can't equalize your condition. So if I wanted to charge a plate or something, a metal plate with electricity, I could take 10,000 volts and I could hit it for just a brief second and it only gets 75 volts put into it. That's all it gets in. I got a little longer, then it's 200 volts. A little longer, it's fine. So it just depends on how long there is whether there's time for a complete sharing of condition where they touch each other and say this was black and this was white, and they touch each other long enough and they all just become gray.
The second law states that objects change their motion when a force is applied.
Alright, so that's one way to say it, yes. And clearly what Newton said right underneath the second law was that 1 unit of force, 1 unit of velocity, 2 units of force, 2 units of momentum, velocity, 3 units of force, 3 units of momentum or velocity. So there's a clear connection between force being essentially understood as momentum. And so you could understand that there can be some discrete object, like photons, that they have some sort of momentum that you might not know, mass, and they have a velocity. And the fact is they're just exchanging an mv, and they're providing an mv. So it's all just about applying momentum, exchanging momentum. That's all that happens in the universe. There's no other event except exchanging momentum. So I don't know what this, to even apply this force in this direction from this side indicating a pull. So here we are again with, Newton I don't think he directly said anything on the subject of push and pull, but obviously it could be understood that, this is so elemental to the first thing you should probably consider is in interactions what can possibly happen. Things can crash into each other, and push on each other, that is, try to move into the space the other object has, okay, but they can't have an interaction if they don't collide. They can't pull. They can't apply a force to the other side and push something into themselves. So that's, it's just so elemental to understand that a push is really easy. You just bang into something, you collide with it, you push. But what would a pull be? And he's drawing it like it's a pull. There's no pulls. The force arrow should be on the opposite side, pushing the object. So again, another pull arrow, not a push arrow from the other side. The forces are always, just as I'm describing, they're like a ray gun of rays, of real little tiny pieces, like a BB gun. That's all something is there's little tiny things that move and hit something, and we call that a force. So it's like a wind. It's like it's actually stuff. Now, unlike pressurized atmosphere or water that sticks to each other, the elemental force bits don't. And so they're not, you have to give them individually motion, like sand. Okay, so would be a better example, because the little pieces of sand don't have to obey any rules. They can get chaotic. Okay, and so the force can get chaotic. I guess that's the way to say it. Little pieces can go anywhere depending on how they interact, depending on what they hit. And I guess I should argue that the force can't hit force. So if a force bit hits a force bit, it's the same difference. If they hit and reflected, you can understand that the universe where they hit, and reflected, would look just like the universe where they missed each other. You'd still have two things moving in the opposite directions, and there wouldn't be any change. All right. Continuing.
An object's change in motion is the strength of the force divided by the mass of the object.
So again, it's yes, it's just a way of perverting perspective, and so it's just mv. It's just the mass moving a velocity, and you're just saying there's two things that have a different velocity vector, and that's the part that's going to get that's going to be part of the exchange. And obviously things that have more mass have more bits with a velocity vector. So if they're going to have a war, the one with more mass is going to win. If there's more black over here than there is white over here, then it's going to be a darker shade of gray. So whatever that is. Okay, so she's very small. She's somehow going to stop it from moving. Blah blah. No, it's not going to happen. So no chance, right? Gigantic mass, very small mass. She's going to lose that contest. She has no way to provide enough force to overcome the gigantic amount of mass, and she certainly can't do it just standing, okay, with a tiny contact to the earth. She'd have to have like steel shoes welded to the earth, and then she'd have to have super powered spring thingy or something.
This means that it is harder to change the motion of objects with more mass.
So why did they use this one thing that looks very massive, and now another thing they call a larger mass that doesn't really look that much heavier? So it just doesn't, you should have a fly hit her and then have a steamroller hit her. All right, so they're arguing that there's a force going this way, and obviously the force is in the CP. It's moving that way in the mass, and now it's going to interact something that isn't already moving, okay, and can't be applying a force, okay. It's just not doing that, and all it's going to do is create like an electrical connection. It's going to allow the voltage in the big object to travel into the ground. It's going to allow the electrons to move from here to there. And in this case, we're not talking about moving electrons. We're just talking about the velocity, the motion, the pressure. So the pressure is going to be applied to the ground. And she's just going to be a wire connecting the two. So that would all be friction. So if we did this in space, all right. So this is time for drawing here. This is the classical misunderstanding. They all, it's so elemental. It's so fundamental, and nobody in physics talks about it. All right. So a lot of these cases should be thought of in free space. Okay, so the space example. And so in this case, we basically just have some sort of circumstance where you have two objects and you have a person, okay, in between, and they're going to apply, okay, some kind of energy to the circumstance. They can store elastic potential, and they can, in any direction, they can create force. We can do that. And so we can create explosions, so to speak. We have a explosive power. So if you did this in space and you had a large mass and a small mass, and you were in between the two, you'd have to give part of the energy to this object and part of the energy to this object. You couldn't avoid that. So you couldn't sit there and say, this is the force I applied, because the total force you applied obviously is this plus the force the other object is going to get, because you're going to push on both of the objects. Alright, so this kind of relates to an experiment where you could have a compressed spring attached to a brick wall, alright, and then launch an object. And it's going to go a velocity. And let's just say the velocity is 100. Now, theoretically, and that's because I'm using a mass, just whatever, a 1 mass, and this is a 1,000 mass. Now, if I do the experiment with a 1 mass and another 1 mass, you can see, oh, okay, half the energy is going to go this way, and this is going to be half, so I'm only going to be going 50 here. Now, the problem is springs can't do this conversion perfectly. So the fact is, when a spring has to move quickly to push something fast, it ends up keeping some of the energy. So you can understand that when a spring expands quickly, when the object leaves the spring is still going very fast. So the spring is going to oscillate with more energy. And if it's pushing something large, it's going to be left oscillating with a lot less energy. So more of the spring's stored energy will be released if it's pushing something slowly than if it's pushing something quickly. So obviously you won't get all of this 50, it'll be something less, 40 or something, because of the inefficiency of the spring. But the simple truth is that you know that you put energy in both objects in this case. So there's the two objects, and there'll just be the oscillating spring in between. And so the point is that when there's a very heavy object, clearly the force doesn't go into the object. Okay, it doesn't get absorbed. It doesn't go into the 1,000 pounds and then into the earth, and it doesn't move the whole earth. None of that happens, because clearly I can increase this velocity dramatically. I can have a dramatic increase in the velocity if I connect it to the brick wall than if I connect it to something where 50% of the force gets absorbed by the other object. So the wall can't be absorbing half the energy. And they actually say it's absorbing 2x the energy, which, again, it's just so crazy. They're saying something hits, and it puts twice the energy into the immovable object. Twice the momentum. So even though the object doesn't move, they're saying twice the momentum went into it, and it moved the whole Earth. That somehow it's moving because the whole Earth is moving. And again, that would be using the force. If the Earth moved, then you can't have, use part of your energy to move the Earth twice as much. So you used 200% of your energy moving the Earth, and you've still got 100% back the other way. That doesn't happen. It's just nonsense. So the experiment just demonstrates that there are things that just reflect, and that's all they do. They don't absorb the energy. And the proof is like I said, I can take the same spring, compress it against an immovable object, and launch an object. And then I can launch the object against another object that does move. And if I do that, I get less velocity going that way, indicating that I am, in one case, giving the energy to the other object, and in the other case of the brick wall, I'm not giving it any energy. So when a tennis ball hits a brick wall, it compresses, it's a spring thing, and nothing goes into the wall. None of the energy is used moving anything in the wall. It all goes into the wall and back out of the wall. It's elastically rejected by the wall. The wall is behaving like a spring. The electrons and protons are, able to expand and contract. So when you hit them, if they don't move and they just deform, if the atoms just deform, they'll spring back. And they're just going to give back in the opposite direction what you put in. They're just going to act like a rubber ball themselves. So they're not going to absorb any energy. They're not going to convert it into heat. They're not going to waste it or use it. They're just going to return it. And, really important. Alright, should probably make a clarification. So this is the circumstance we start with in space. And my argument is that if you did this experiment where you're just pushing on two objects and you just keep increasing this mass, so you make it bigger and bigger and bigger, there's a point where you'll reach a point where this mass won't get half the energy. It won't get half the momentum. It's going to be less, and then a point where it's just going to be zero. And then all the momentum is going to go into this object. And that's, like I said, clearly what the experiments show. So if you do that experiment where you put a spring on an object that can move, and it moves, then this object goes with less speed. And this object, if it's the same object, and you put it against something that won't move, it will leave with a higher velocity. Even though the spring is less capable of pushing things at a higher velocity, it'll still go faster. It'll go better faster if springs were more efficient at pushing things any velocity. But they're not more efficient at pushing at any velocity. Obviously, we can't push things faster than the spring can expand. So anything light enough to go faster than the spring can expand, the spring can't make it go that fast, obviously. Alright, back to the video. Alright, so now so the large object has applied its greater momentum. She's just been a conduit. She can't push on it because it's got more energy than she has, and she just ends up giving the energy to the ground. Then there's a point where you've absorbed all the energy into the ground as friction, and now she's going to apply a force, an expansion force, and attempt to give it motion. So now she has to again use friction to create a reflection, something to reflect off of. And now she's just going to say, basically, I'm going to push this way, and the energy is going to reflect, the energy I'm pushing on the immovable object, the Earth, has to remain immovable. If it moves, then I have to use twice as much energy. So that's why they think there's twice as much energy, is because they're calculating both things moving. So you start with this much motion and you somehow have twice as much of it. It's like you gave away the money twice. You gave $5 to the Earth and then $5 to the object, and now you've lost $10. Okay, when the point is there's only $5 in the thing you pushed. But you can put the full $10 in the thing you're pushing if you're stuck on an immovable object. It's just going to reflect the energy. So they're saying here the Earth is getting moved constantly in the opposite direction as the thing is moving in this direction, and that's not happening. The Earth isn't moving, and the whole point is the reason and the fact that it's not moving is the reason why you're capable of moving the other object. Because if the Earth did move, if the Earth was incredibly light, if she was walking on styrofoam beads or something, then she couldn't push the other object because the beads would move much easier. So whatever thing is easier to move is the thing that's going to get moved. And the thing harder to move is the thing not going to get moved.
When all forces are removed, the object's speed will stay constant.
So that's just saying the first law all over again. So it's has very little, if has no relevance, okay, frankly, to this example. So it's pretty incoherent. It's redundant and incoherent. And this is not
If we watch the
useful. Okay, so here we go. So let's play it.
previous scene again, we will see that the moment Victoria exerts a force against the train instantly also exerts a force on her.
So doesn't happen. So again, the force is just, there's one element that has the imbalance causing the collision, you could argue, and it's the object that has more momentum, and it's going to share its momentum with what it's interacting with, and the only way she can possibly prevent that is somehow to have more momentum, that is, be part of the earth and be made out of tungsten or something. So there's not two forces. She's not applying a force. There's just the force draining into the earth. That's it. So the velocity portion is draining and giving velocity to the particles of the earth. And if you add up the NV that's in the object moving and then the MV in the particles moving, it's the same MV. The MV is just draining into the earth.
This is what causes Victoria to move backwards.
So she's caused to move backwards because she isn't making good enough contact with the earth. So she's basically sliding across the earth. She's not stuck to it. She's not part of it. And so it's just friction. So she has a very solid contact with the thing hitting, and she has a very not solid contact with the earth on the other side. And she's just slipping. Which is still draining the friction. She's still draining the energy through sliding across the earth. Yeah.
The two forces are exactly equal in strength.
So there's no two forces. It needs to be said. There's no such thing as a force of friction. There's no force of friction. She's draining the energy. She's transferring it from CP. She's just being used as a stick or a piece of metal or some little thing in between. And just like in a Newton's cradle, she's just one of the balls in the Newton's cradle. She's just transferring. She's just being used as a conductor of the force into the ground.
And they are in exactly opposite directions.
So there is no opposite force. There's just the transfer. The CP has the $10. It's now draining it into the earth. And it can give all of it away or a portion of it away, depending on how well that contact and how long the interaction lasts. Obviously, in this case, it's going to drain all of it. And it's not going to be converted into the earth moving. It's going to be converted into a bunch of little pieces of the earth moving in all kinds of directions. So direction makes no difference. All directions are momentum in a direction. So you can't make a bunch of pool balls scatter. You put one ball in and you hit the racked balls. All you can do is give the MV that was in the cue ball to spread over all of the racked balls. You can't give any different amount. Well, the two will have to equal. The before picture will have exactly the same mass moving as the after picture. There won't be more mass moving. So the little bits moving is essentially heat, and that's already used the energy. It's gone. You can't use it twice. You can't move the earth and make the little pieces vibrate. You can't do both.
Third law states that for every action, there is an equal and opposite reaction.
So it could be that it's just another action, okay? So you could say interaction. You could state that for every event, there's an opposite. So if I give away $5, obviously I have been changed. So for every change, there is an equal and opposite change somewhere else. You can't ever... I can't make something more white without me becoming more black. So it's just wrong to imply that friction is a force and that it's some sort of equal force. Not true. And it's really not what the whole concept is saying, which is there's in all cases where you're going to create force, I mean, the most obvious one is an explosion. Obviously, the action happens in all directions equally. So, right there it's saying it. And then again, if I use the interaction, $10 of motion, it gives away $5 of motion. Well, now it only has $5 of motion.
When Victoria's feet move against the earth, she is creating the force pushing her forward.
All right, so she's not creating the force by her feet moving forward. I mean, it's the fact that she's trying to create a contact with the ground and a contact with the force, and then she's going to do this expansion thing. She's going to contract and then expand, and that's going to be the applied force. And again, in this case, the applied force is against something that's not going to move. So all the energy being applied to the thing that's not going to move is going to get reflected. And so all of the force will end up going that way. The spring can't expand both ways. Then it just expands the one way. Let's just say it goes where it's easier to go. It moves in the direction of the lighter object. So as the spring's expanding, if there's less pressure this way, it's pushing something lighter, essentially the center of the spring's mass will move in that direction.
Victoria's feet moving against the earth also creates an equal and opposite force pushing the entire earth in the opposite direction.
So that just doesn't happen. All she's doing is heating the ground, essentially. She's pushing the atoms in the earth. She's jiggling them. And that's the wasted energy. The less she jiggles them, okay, the more solid her contact with the earth, and the less transfer of energy, the more energy gets into the other objects she's pushing. So it's more efficient to create no motion in the earth or in its pieces. Yeah, I mean, it's obvious. Yeah. You can't use the energy twice. You can only, you can only convert it. And as soon as you have pieces moving of something, that's the same as the something moving. So if the pieces are moving, that's the same as moving the something. But you can't move the little pieces and move the big object. So if the little pieces are moving in chaotic directions, the momentum's gone, and it can't be doing this. It can't be going all this way when you're conceding it's going in all different directions. It doesn't happen. So the Earth doesn't spin faster. The Earth doesn't do any of those things. None of that crap happens. So this is illustrated by this classic experiment. Again, yeah, I might as well draw it. All right, so this is, just a huge giveaway. Physics really doesn't know what it's talking about. So I can take an anvil, okay, heat treated. So that means the surface atoms don't move. Okay, so if I used a regular steel anvil, when I bounce a steel ball bearing against it, I actually dent the surface. So I actually displace, deform the anvil and make heat, and then the heat dissipates. So I use the energy and I don't get much back. Okay, I get a small return. But if I heat treat it, I can get a 99% return. So the ball bearing goes in, it comes back up, and I can get 200 bounces. All right, and what they're arguing, what physics is saying, what he's illustrating here, is he's saying every single time that ball bearing bounces up and down, somehow it gave twice the energy, twice the momentum, the MV. So there's a certain MV when it hits the surface. Somehow it gave 2x that amount of MV to the anvil, and because the anvil is connected to the Earth, to the entire Earth, and it's pushing the Earth with twice the momentum. So the Earth actually moved with this infinitesimally small but real velocity increase. So I really gave the Earth more velocity. And again, I got all of my energy back almost, so I can just keep redoing it over and over and over and over. So I put 1 unit of MV in, and I get 1,000 times more MV out. Okay. Which makes 0 sense. So it's not conservation of energy. So the easy answer is yes, the key to the experiment is the surface. And if the surface can't be heated, that is, I can't dent it, deform it, inelastically affect it, then it's perfectly elastic. So the trick is the word elastic, and we understand it in the concept of, you have a rubber ball and you can deform the rubber ball and it springs back to its original condition. So you're basically just taking something like a spring, you're compressing it, and then it's going to go back to its native state and release the energy as a reflection, essentially, right? You push in and the spring just reflects the energy and pushes back out. Well, the key is that, that form of elastic isn't that far from the truth for these hard steel objects, in the sense that their atoms are elastic. The position of the electrons, when you push on the electrons, it pushes on all the electrons, and they essentially all compress, and they're all going to want to go back to their original condition. So they're going to behave like a spring. It's just this infinitesimally small spring, it's a tiny, tiny difference at a very high speed that the electrons are interacting with each other. So when two things hit each other, the electrons are all vibrating, and so they're all hitting each other at much higher speeds, and all kinds of that kind of things interacting. And so those little tiny motions end up, when you do trillions of them, end up into big motions that we see. But the simple truth is, the anvil is a reflector. Okay, it's going to reflect the energy you put in. So anything you throw at it, it's going to bounce it off. It's going to reflect it. Whether it be a ball bearing or a rubber ball, it doesn't matter what you throw at this surface, as long as it's not harder than the anvil's going to reflect it. There's no transfer of the momentum. The momentum is essentially rejected by the surface, and that's what creates the reflection. That's why the ball bounces back. Again, their theory is that the more the wall yields, that is, the more energy I put into the wall, 2x, up to a maximum of 2x. They have an experiment where they do this thing with a 1 mass hitting a 3 mass, and it creates 150% of the momentum increases. Can't happen. It's free momentum. There's only so much of this little stuff in the universe. There's only so much motion. If I have a bunch of vibrating things, I can only make something else vibrate with the amount of vibration I started with. I can't make free money. There's only so much of the currency of motion in the universe, and all you can do is change the objects that have it. but the motion is elemental to, the amount of force in the universe, and you can't change that amount of capacity to move mass. Yeah, so the point's made. The anvil doesn't move, the earth doesn't move. The reason why you're getting more back is because it rejected the transfer. It said, I'm not taking your $5. Here it is back again. That's the simple truth. The little object comes in, it hits with a $10 bill, says, take my $10. The anvil says, nope, I'm not interested, and I keep my $10 and go the opposite way. It's obvious.
Because the mass of the Earth is so large, the impact of this force on the Earth's motion is extremely small.
Right, so they're saying it did two things. Okay, you got the reflection, and you put the money in the object. So you keep the $10. You have a mass moving with a velocity, your reflection. You kept all your money. You just changed your direction. Changing direction means nothing. Levers do it all the time. Gravity does it all the time. You throw something up in gravity and it throws it back down. It changes the direction. Happens all the time. But you can't make extra. You can't have $10 going this way and $10 going that way. You can't make money. You can't make the currency of motion. You can only transfer it.
For larger forces, the impact on the Earth's motion is no longer negligible.
So for larger forces, which would be like a moon colliding into the Earth, obviously it has enough momentum not to be reflected. So there won't be a pure reflection. The moon won't just bounce off with all of its momentum. It will deform the Earth, it'll move matter, and all of the atoms will agree to go somewhere because there'll be enough momentum provided. What other force? You could argue that the sun's gravity moves the Earth, okay, and it does it by the Earth actually absorbing the force. It's just a fact. It absorbs force based on the density of its mass, its atoms, the number of electrons and protons. Their motion is an absorption of force.
According to the first law of motion, the Earth will want to continue moving in a straight line.
All right, so this is really bad wording, this wanting stuff. So obviously orbits are just made out of two interacting forces in the sense that you have a force, your vector of motion, and you're just going to add a force to it. And the constant force is being added sort of irregularly in the sense that you're moving through it and you're changing your proximity to it. And so it constantly is changing your orientation to the spherical body. So you just, you could just argue that you keep going in a straight line, but you're being pushed down, but you keep missing the Earth because it's round. So you have to keep falling down. Now the interesting question I thought of in thinking about this is they call this free fall, like if you have a person in space, okay, and then they call it weightlessness. So there's different ways of describing the fact that they're weightless even though they're still in very strong gravity. So the gravity doesn't change significantly for people in space. It's not less than 9.8. It's pretty close. But you have to go more than 4,000 or 10,000 miles to significantly change your gravity. So they're still being affected. But the truth is they're not accelerating. So weightless would make sense to say, but free falling wouldn't, because free fall you're gaining velocity. But when something's falling in a gravitational orbit, it doesn't gain any velocity. So even though the Earth keeps being pushed in towards the sun, it doesn't go faster and faster and faster and faster. So there's something using up that acceleration where it can't keep accelerating. So even though it's a constant force, constantly pushing, it somehow doesn't gain velocity. It's just an interesting fact.
According to the second law of motion, the gravitational force from the sun will want to cause...
So again, it's drawn as a pull force. All right, the forces should always be drawn as pushes, because that's what the universe is really made out of. There are no pulls. There are no elemental pull functions in the universe. The universe can't just come here. It can't make that happen. Something has to cause a push for there to be anything that looks like a pull.
The Earth to fall directly into the center of the sun. Note, in Einstein's theory of relativity, gravity is not a force but a curvature.
Right. So why bring it up? If you're going to play the game, so why don't you choose a way of understanding it? Because it's clear. There's a clear difference. I mean, recognizing that it's a real mechanism in the real universe, and then just calling it a bent geodesic, somehow empty space is bent, isn't a force, it isn't a mechanism, it isn't a physical thing. It's incomprehensible goop as an explanation. So yes, you should recognize that, yes, you're going to understand it as a real force, and then you just have to understand, if I put this arrow on the other side of the Earth, the simple argument is that in the interaction between the Earth and the Sun, they're basically casting shadows on each other. They're absorbing energy. So as energy goes through the Earth, it heats the Earth, exchanges its momentum, and so less force comes out of the Earth than went into the Earth. So if I drew the red arrow on this other side of the Earth and made a bigger red arrow, just sort of indicating that stuff that was going to hit the sun isn't going to hit the sun now, because it's delayed heating the Earth. And the sun likewise is in the shadow of the Earth. Now the Earth's shadow is a lot smaller, and so the two things end up equaling out, and you could say it's an equal and opposite, but it really isn't. And it's just the law of proportions, and obviously the sun is going to cast a darker shadow than the Earth is, so to speak, bigger and darker. Let's see, what else is there to say about that? But it is interesting, again, that the Earth, even though it's in that constant shadow produced by the sun, and it's constantly being pushed towards the sun, it doesn't gain any velocity. It keeps moving the same speed. So I guess you could argue that the velocity is used up by the extra distance it has to travel. And so because it's going straight and it's going to have to turn, and this is more distance, that diagonal line, you could argue, is longer than this straight line, and that used up the velocity.
In space-time. This will be discussed later in this video. According to the third law of motion, the Earth will exert an equal and opposite gravitational force on the Sun.
So in a sense, it's as it orbits, it's taking some velocity and then giving the velocity through the forward motion. So the Earth actually has to speed up a little bit to compensate for the longer path it's going to have to travel. So it's not going to do the straight line, it's going to do that curved line. So because of the longer distance it's going to have to travel, it stole some of the velocity, but it gave the same velocity with the increase from the gravity. So it's just it's constantly traveling more distance and changing its speed to do it. So yeah, so the speed is constantly changing. So it accelerates and then decelerates and accelerates, and so it looks like a consistent velocity, but it's really accelerating and then decelerating and accelerating and decelerating.
Since the sun's mass is much bigger than the Earth's mass, the impact on the sun's motion will be negligible, but the impact on the Earth's motion will be significant.
So it's just about the density of the object. Again, the whole idea is that a particle gravity theory is just basically going to say that the 4 bits go into the Earth. They're going to interact with all the atoms. So the number of electrons are the key thing, the little bits, the elemental bits. So the denser your material, the more interaction there's going to be with the force. So obviously heavy things collect more force, that is, they're more opaque, and light things are more transparent in a sense, and so they'll collect less. So it's like having a sail made out of strips with a bunch of open space, and then a sail made out of solid material collecting wind. So the lighter the material, the less wind collected. The heavier the material, the more solid, the more elements of fabric, the more wind prevented from getting through. All right. So gravity doesn't have to figure this out. It's just elemental that something transparent okay, doesn't collect as much of something as something opaque. It's harder to hit I don't know how to yeah, harder to hit. It just look, it's it's just the difference between something with holes in it and a strainer and a solid funnel or something. Yeah, more holes, the less transfer. The less holes, the more is transferred. All right, so we're over an hour, so I guess we'll call this it. It gets into rotational stuff, which is interesting, and then finally into the whole Einstein crap, which is just terrible. Yeah, some of this stuff might be worth coming back to, so I'll decide. But I got a Professor Lewin video to do, and a science and math guy one, and another different one of these Eugene videos. So anyway, so we'll just call this a video and such. So this, I'll title it the lever paradox, because again, this just relates to the whole kinetic energy theory. And the fact is, I don't know if he has a lever video. I haven't seen one that I remember. And this whole claim, it's Steve Mould, a guy who gets millions of views for videos, is claiming that levers don't conserve momentum and that they don't obey the law of the lever, and no physicist objects, finds that in need of clarification. They just buy it, that somehow a two mass going one velocity will not produce the same momentum on the other side of the lever. It won't produce a one mass going two, when that's exactly how it will oscillate. I mean, it's incredible that I'm the only person arguing that you can't say that credibly. You can't make a credible argument that levers don't conserve momentum. It's just so incredibly wrong.